This is going to be looking at some of the mathematical relations that we'll use for sound. Not all of them. We'll come across others later, but it'll just be some of the equations we're going to use and some of the ideas that are going on in here. First of all, sound is a longitudinal pressure wave. The displacement of the air molecules caused by a wave is along the direction of travel of the wave. And here's a place you can see an animation. I'll have this link in other places so you don't have to copy it down right now. Okay, here's this animation. The top part of the picture here shows how this wave might be produced. You might have a tube, and at one end of it is some sort of a device that's going back and forth and generating these waves. And when it's going to the right, it's generating a point of high pressure. When it pulls back to the left, you end up with a diminishment of pressure. And so you can see that. Now, an important part about waves is that it's a way that energy is transferred without net motion of the medium. And if you pick any spot, any one of the dots that are on there, and look at what they're doing, they're just going back and forth in place. And they've got a few of them marked with as red, and you can see how they just go back and forth there. Also, you can see on the bottom picture that there are a series of compressions. You can see the dots are more crowded on those. And then in between those, halfway is a rarefaction where the dots are less crowded than average. Excuse me. So you might want to just come back and stare at this thing some, but we'll head back to here now. Excuse me. Okay, so first thing we'll look at is an equation that describes the longitudinal displacement of the air molecules. This is different from the one in your textbook. It's actually, many other textbooks use this form of it that I have here. Your book has it written as y of x and t is going to be y max cosine of kx minus omega t, which is the equation we used for a transverse wave. But in order to not have it be inaccurate, the author of your textbook says that y and x will be in the same direction for this. And I find that kind of confusing. So we'll take some measurement s, which is in the same direction as x, and it's going to look like this. And s sub m will be the amplitude of the displacement. Now you've got that cosine term in there, and when you look at how that's going to change in space or in time, it's going to make something that goes from +1 through 0 down to -1 and back up, and it's going to be varying sinusoidally is what we call it, or cosinusoidally, it's the same thing. And so that s of x and t will be a back and forth motion of the particles, and you just saw that on the animation. You can also write the sound wave as a variation in pressure, and we get delta P equal delta P sub m. Delta P sub m would be the amplitude of the pressure wave. Now, your book doesn't have the deltas on here. It just writes P equals P sub m sine of kx minus omega t, and they say P is the pressure difference from background pressure. I like it better with the delta on there, and most places you look, they'll have the delta on there, because the delta P is the difference in pressure between that produced by the wave and the ordinary background pressure. Ordinary pressure at sea level, the average is 1 atmosphere. As you go up in elevation, it diminishes, but that's what it is. And it's 1 atmosphere is defined to be a particular number, and it's 4 significant figures. This is what it happens to be. Pressure is force per unit area that's produced by the air. You might be familiar with atmospheric pressure, or you may have heard 14.7 pounds per square inch. Again, that's at sea level. It diminishes with altitude. But this is what it is in newtons per square meter. Square meter is much larger than a square inch, and a newton is less than a pound. So when you take a combination of those two things, you end up with 101.3 thousand newtons per square meter. And that combination of units on there, the newton per square meter, is defined to be a Pascal. And if you write out the word, it's lowercase. If you have the abbreviation, it's an uppercase P and a lowercase a. I usually like to keep track of what the units are, so I just write it as a newton per square meter most of the time. But we could do the Pascal, and the 1 atmosphere pressure is sometimes written as 101.3 kPa, or kilopascals. Okay, we have the S of x and t equals S max cosine of kx minus omega t. And here's the delta p looking like that. The fact that one is a cosine and the other is a sine means they will be out of phase with each other. And here's a graph I made, and it shows just what a cosine wave would look like. Up at this point, oops, I have to turn this into a writer. Up here is where the displacement would be S sub m, and then it drops down to 0. It goes down here, it would be minus S sub m down there, comes back up to 0, and keeps going back and forth between those extremes. Meanwhile, the pressure is doing something different. When the displacement amplitude is at a maximum or a minimum, at both of those places, the pressure amplitude is 0. There's no difference from the background pressure. And it's when that displacement amplitude is at 0 that the pressure amplitude is at a maximum. So you have this back and forth going on, similar to the way there is a difference between the displacement and the particle velocity or the object velocity for a mass hanging on a spring. But you have those two things being kind of confused that way. Also, you might imagine that the greater the pressure amplitude happens to be, the greater the displacement amplitude will be, and vice versa. And so we have this going back and forth between the two things. Now, I'll introduce what these things are a little later, but v is the particle or the wave speed. This is the Greek letter rho. It's kind of like a scripty p, but it's the Greek letter rho. That's the density of air. And then omega, of course, is 2 pi f. So a frequency term there. Okay, now we'll look at the energy delivered by sound waves. And we can express this in 2 ways. One is the decibel level, and I'll describe that a little later here. The first way that we'll actually look at in some detail is the intensity. And intensity is something that shows up quite a few places in science and engineering. And it's usually the power delivered per unit area. And so watts per square meter will be the units of this. In astronomy, we talk about the intensity of light delivered by something like a star, and actually out where we are, as far as we are from the sun, we get somewhere in the neighborhood of 1,300 watts per square meter delivered by sunlight. Now, that's not going to be what you get on your solar panel necessarily, because it can drop to close to zero if you've got heavy cloud cover or at night. And also it depends on your latitude and how you have your solar panels oriented. And also some of the power is absorbed going through the Earth's atmosphere. So that can be different. There's another place in astronomy we might talk about intensity, and that is something that depends on the surface temperature of a star. The higher the surface temperature, the more intensity there is for light coming off of the surface. And there we'll measure the intensity of light given off by an object of a particular temperature, and it's how much power per unit area that object is radiating. So that's someplace it can show up too. Here's the expression for the intensity delivered by a sound wave. And we'll look at this equation in a little bit more detail here. But you can see one thing it depends on is the square of the amplitude, either the displacement amplitude, the S sub m, or the pressure amplitude, the P sub m. And so there's some things it depends on. Also about the wave intensity, it diminishes with distance from a source. And most of the problems we're going to look at will assume a point source, and then the sound wave energy is being distributed in every direction from that equally. So when that's the case, that intensity that looks like that, it's going to get smaller as you go farther out, which means the displacement amplitude and the pressure amplitude will be diminishing with distance from the source. But the things it depends on, the air density, rho, that Greek letter, the wave speed, v, and then the frequency, omega equals 2 pi f, and the square of the amplitudes. Now, the way it depends on distance, we'll assume a point source and equal distribution in every direction. And the power of the source ends up being spread over a sphere in the space surrounding the source. And the intensity of the wave will then be P, that'll be the power of the source, divided by 4 pi r squared. The formula on the bottom is the surface area of a sphere, and that power will be distributed all over the surface of that kind of imaginary sphere in space surrounding your source. And we'll do some example problems that show this. The second way of measuring in the intensity of a wave is called the decibel level. And when we measure the I, that's the power divided by the 4 pi r squared, we call that the sound intensity, and we measure it in watts per square meter. For the decibel level, we use a Greek letter beta, and it ends up being a dimensionless quantity, and we use the sound intensity to calculate it, but we make it into a dimensionless quantity. I'll show you soon how that looks. The decibel level is called the sound intensity level. So the sound intensity is the I, that's watts per square meter. The sound intensity level is dimensionless, and we denote that with the beta. And I'll show you the formula here for calculating it. Beta is 10 dB, and dB, a lowercase d and an uppercase b, is the abbreviation for a decibel. And it's the logarithm of I over I naught. Okay, the I is the intensity, and I naught is defined to be exactly 1 times 10 to the minus 12th watts per square meter. And the reason we use this level is because it turns out, and it mostly revolved around human hearing, humans can hear down to an intensity level of about 1 times 10 to the minus 12th watts per square meter. Now, that varies all over the place with age, the quality of your ears, just all sorts of different things. But they just decided to define I naught to be exactly 1 times 10 to the minus 12th watts per square meter. And with that, you'll be dividing whatever the intensity is by that. But humans can hear 1 times 10 to the minus 12th watts per square meter, but they can hear up to intensities well over 1 watt per square meter. Actually, at that point, it starts to become damaging to your hearing. But because we can hear over such a huge range, they decided they needed to find a way to shrink that range. And so they came up with this decibel level. And inside the parentheses on that formula up there, I over I naught, you'll have watts per square meter on top, watts per square meter on the bottom, and you end up with a dimensionless quantity. And that's how it's calculated. And we'll do a bunch of calculations with this. Okay, that's the end of that.